All right. In the previous record video which is to cover for the chapter one, the main part. From today, we're gonna really basic signal properties, DC, RMS, DBM, and the power. We classify four different sessions for chapter two. That is the one of them to the start. Okay. All right. So now we are in chapter two, signal and spectra, and hopefully after end of the chapter, we're gonna do quiz two, and after that, we're gonna do the test. Okay. I will keep in mind. Really, yeah. Okay. All right. So the session 2.1, the chapter 2.1, just only for cover, really basic of the signal systems, the basic properties. Okay. So maybe again, that was the homework. I will not checking, but you have to do all the questions from the test. In the is the came from these questions. Okay. All right. So properties of signal and noise. Okay. The communication systems in the communication system that receive the waveform uh, means the after passing through the channel, which include the noise, a lot of multipass, as a finally usually categorized into the two part. The one is signal, the other one is the noise. Okay, the signal is the desired part of the waveform containing of the informations. That is what you wanted to do. Okay, but the noise, there's a lot of type of noise, but the noise could be defined as the undesired, the part of the waveforms. Okay, and the signal, the receive the waveform, the signal, we're gonna the W over the T. Okay, that was sometime the desired signal that was include the informations what we wanted to do with the noise. So the finally we're gonna reject or remove the noise and successfully to reconstruct of the original the transmit signal. That is what you wanted to do. Okay. So a lot of the function and operator, but the time average operator is very important. The time average operator this is the sign right there. Here it was limit t to the infinity. Okay, just the infinity 1/t. Okay, okay, that was t over t minus t over t. So function the average and time. This is the integral, the average value. The t is going to infinity. Okay, this is the time, the average, the operator. Okay, time average the operator. So that operator has function two characteristic of the linear the operator. Okay, the average sum of the two quantities is the same as the sum of the average. Same thing like this one. So a sub one and a sub two is like constant. It should be going outside. So the one of the receive the signal, the w sub one over t and w sub the two over t. Yeah, definitely we're gonna apply to time average operator for the each the receive the signal. That was the same function. All right, so the waveform, the W over T, Professor Y W over T, this is from the books that was defined. There's a lot of definitions possible, but the waveform W over T is the periodic with the period, the T sub 0 for all the T here, okay? So T sub 0 is smallest positive number that satisfy the relationship, okay? Sinusoidal, the waveform of frequency F sub 0 is equal to 1 over the T sub 0 hertz is the periodic, okay? So So really the basic. Okay. So if the waveform invert is the periodic, the time average the operator could be reduced like this one. Okay. So that is really the simple theorem, periodic waveform. Um, Again, that was the summarize from the previous slides. So that the first formula for the time average operator, they calculated the average maybe over all the time. Okay. The all the time because the limit is going to the infinity. But the second formula for periodic the waveform, kind of sine wave or rectangular, doesn't matter. Calculate the average over one period of the periodic the signal. One period. Okay, it's very important. So usually in the questions that was the second form, but sometimes yeah, definitely the time average the operator, but the periodic waveform as well. All right. The DC value, DC power, value means this voltage, current, and power. The values, a lot of values. The DC means the current. the direct current. So this value waveform of omega t is given by is the time average W over t. So W dot C is the time average operator. It's like this one. Okay. So physically waveform, we're actually interested in evaluating this value only over the interval of the interested. Yes. Okay, this is the period form. So from t so 1 to t sub 2, just like this one. Part. So again, the V over T, if, we assume that V over T denote the voltage across set of circuit terminals, and let I over T the denote the current into the terminal as shown. We're gonna just instantaneous power is at the incremental work divided incremental of the time. The specific time we're gonna divide it is like specific period, T sub to 0. So in here, just only the V and I, the V over T times I over T, that was the P. It's right here, it's right there. So that was supply means the power from the circuit to going outside, we're gonna supply, we learned before, the minus P over T. Yes, definitely the observe, that was the plus the P over T. We're gonna learn before in the circuit and also power system courses before. The average power that was for P and time operator and P over T. That was the function of the time, the real time P over T. That was V over T times the I over T. Okay, so that was the limit. T is going to infinity, 1 over T, T over 2 minus T over 2, and P over T and dt. Okay, all right. So that was the RMS value. That was root mean square value of omega t. WT. WT is received waveform signal. Okay, signal. Receive the signal. So the WRMS is simple. Right there, RMS, root square, and the average operator we're going to apply. So, for example, the RMS value of a sinus waveform, the V cosine of omega sub 0 t square root is equal to V over root 2. V over the root 2. The V is the peak voltage. I'm going to show you the later, make a derivation, but in here, just, definition to make it clear. The theorem is if a load resistivity under condition in 90 power factor means cosine theta is 1. The average power is V square of T, average the operator is R, or I square the over T, the R. And if you know the RMS value, V sub RMS square over R, I sub RMS square is R. And sometimes also V sub RMS times the I sub the RMS. That was the average power value. If when R is value of the resistive, the rod. So again, the RMS value could be defined as square root of the average of signal. The period, for example, mathematically for a periodic the signal f of t with the period t sub 0, the RMS value was given like this one. Okay. For example, this is a sample. So the given signal f of t, for example, v, the peak value, and cosine of omega 0 t. Yeah, this is the angle frequency. This is 2 pi f sub 0, 2 pi over t sub 0. Okay. So the step one, substitute that signal into the RMS value right there. So v squared, that was constant, so we can go outside. Okay. All right. Some student has been confused again. T sub 0, 0, it doesn't matter. Okay. Minus T sub to the 0. Doesn't matter. So use trigonometry identify for cosine square over x. We're going to learn before 1 plus cosine 2x over 2. And that one substitute these expressions into the integral, right? This one. Okay. So split the integral like this one. Okay. So thank you. Answer. All right. So in the here, the first term is going to t sub 0, and the second the integral that was we learned before, that was the period. The periodic signal, like a sine and cosine, have infinity. That was repeat identically. The overtime that was going to 0. Okay, 0. Right? Because okay. Because again, the term cosine of 2 omega sub zero t complete one or more for the cycle over t sub zero, and is the positive and negative area that cancel out. So this is why. Okay. So finally, the remaining the cancel t sub zero, and that was root v square over two, root two over v. So that was simplify the answer for from the value. Okay. All right. That was sorry about that. That was for simple question, very simple questions. 120 volt, 60 hertz fluorescent lamp while in a high power factor configurations. Assume that the voltage current are both sinusoidal and are in phase. United power factor, I mean cosine pi is going to 1. So now the DC value to question 1. Sorry, this is the DC value of the periodic voltage waveform. This is important, periodic voltage waveform. So that is formula V sub DC, V of T, the time average operator here. That was for 1 over t sub 0, t sub 0 over 2 minus t sub 0 over 2. We learned before that was the cancel out positive negative value, maybe over the period, the full cycle. Right there is going to 0. Okay, this value is going to 0. How about the instantaneous power? Instantaneous power is just v cosine omega 0 t times I cosine omega 0 t. Vi, the cosine 0 square. Vi cosine 0 square omega 0 t. That is what? 1 plus 2 cosine omega 0 sub 0 t. Okay? The 1 over 2. So that is for instantaneous power, the function. How about the average the power? The average the power we need use for the time, the average time, the time average the power. We're going to go back to here. So right there. There we go. Okay, so that was time average power. We learned before time average the operator. Okay, so that is what we wanted to do. All right. So, oh, sorry. But that was the period the waveform. We have to divide it 1 over what t sub 0. Okay, here. So just to plug in here. So finally, we learned before to cancel out over the period, positive, negative part. It's going to 0. So only the 1. And finally, the VI, the over 2. Okay. All right. So I'm going to just in here. Maybe after we find average the power, this all V and I is like peak value. V sub P, I sub P, peak value right there. Okay. So all of them. But however, the maximum power, this like the power is when we calculate the maximum power, that should be the RMS value. Okay. So we're gonna be changing the RMS value, from the peak voltage and peak current to the RMS voltage and RMS current. V sub RMS is equal to V sub P divided root 2. I sub RMS is equal to I sub P over root 2. The V sub P is equal to root 2 times V sub RMS, and I sub P is equal to root 2 times I sub RMS. So root 2 times V sub RMS, root 2 I sub RMS, divided 2 from the answer. So this Y, the peak value that was the power is V sub RMS times I sub RMS. Okay? All right? Thank you. So, oops. Okay, so the question 2, function generator, we learned before, define the DC value. So 3, 2, minus 1. This is the T, period, right? So V sub DC, the 1 over 4, it's right there, V over T. The V over T is the area, go back to here, 2 times 1, the multiply the 1 over 2, okay? And then the minus 1, the times the 2, the other period, right? This one, I'm sorry. Here, 2, the times the minus 1. So, and still the 1 over 4, that's the period, the finally minus 1 over 4 voltage. The other one is, the question was to find the value for RMS voltage. Okay, the RMS voltage, that was the function for 1 over t square, 1 over t sub 0, and integral the t, and the function square, the dt. Okay, we're going to skip the root because they did not yet removing the square from the original V sub RMS square right there. And in here, we're going to just symmetric curve, the based on the zero. So we're gonna to the change the 2 times 0 to the minus 2 or the 2 to the 0. It doesn't matter. Oops, sorry. 2 to the 0. It doesn't matter. So the 2 over t sub 0, the t sub 0 is what? It's like 4, but just now 0 to minus 2, v sub square, minus 1 minus 2, minus 1 square, right there, plus 0 to minus 1, the t plus 1 square. Okay? All right. You understand in here? Oh, I'm going to show you. So minus 1 minus 2, minus 1 minus 2. It's right there. I'll show you. Oops. Minus 1 minus 2, that was the minus 1. But the minus 1 to the 0, that was is what? Minus t plus 1. Okay? Oh, I'm sorry about that. Not minus t, because that was the plus t. Because the x derivation, y derivation is like the plus, that was the plus 1, the increase, y1 also the plus 1. So 1, the slope is 1. Okay? That was the t. Yep. So in here, that is function. So the after the calculations, the finally that was the 2 over 3. But we begin to v sub RMS the square. So we're gonna the root. So after calculation, 0.816 volt. And then the last questions that was for if the voltage waveform is applied to 1,000 ohm. We're gonna using the ohms law, but they're looking for the power dissipated in the rod. So when the register, that was the formula V sub RMS square over R. There was the 2 over 3 over 1,000. So that was 0.667 milliwatt. Just after calculation. Okay. All right. So yeah, so that is the one more time. That was the not one more time. That was the that slide introduced to the average and normalized the power. The other one, the total normalized the energy. The average normalized power is given as the following function. Again, we learned before the W of t was the signal. Receive the signal. Receive the signal is possible to voltage over currents, the waveforms. So in here, the power, again, the W square of t, the average, the power of the operator, that was the limit to the infinity, but that was dividing specific period. However, the total normalized the energy that was not divided the 1 over t. Okay. So from these slides, we're gonna just introduce about the total energy of the signal, V of the signal. So this is why we're gonna learn in here. So the total energy of the signal measure how much work the signal can do over all the time. Mathematically, it could be calculated by squaring the signal value at each moment, assuming the square of all the time, considering the limit as the time interval approach is the infinity. That's the infinity. So the formula, summing up the scale value, similar from to minus 2 over 2 to t over 2, consider the limit as t become to infinity large. Okay, so that was the energy, the formula, the total energy formula, especially for the signal. How about the average power? So via the total, the energy. Okay. So the average power indicated how much energy the signal delivers per unit of the time on average. Okay. So it could be calculated by taking the total energy over a time period, dividing it by the length of the period, they're considering the limit as the time interval approaches infinity. So that was for the same scale of the function of the time, but however, again, it was only different 1 over t compared to the total the energy. Okay. Okay. All right. So that was for the sample the questions. We have to distinguish that function is what is the total normalized energy and what is the average normalized power. Okay. All right. Just a second. All right. I'm gonna write it for you here. Um, so here, so total energy first. That was for the formula non-periodic minus infinity square the dt. Okay. Um, the average power that was 1 over t square and dt. Okay. So that was for the normalize. They include the normalize. We're gonna to include limit t infinity. Okay, if the concept is normalized. Oops. Okay, so the given signal, the W over T 5 cosine 2 pi T. Okay. So the square was square and 25 cosine square 2 pi T. Okay, so we long before here, that was 2 over 1 plus cosine 4 pi T. Okay, so that was the trigonometric identity. So we learned before the average normalized power in here. I'll show you. That was 2 over 25 plus 2 25 cosine 4 pi T. Okay, so P is 1 over T, 0 to T, 25 over 2 plus 25 over 2 cosine 4 pi T, the dt. Okay, so that was going to 0. We learned before that finally that was 25 over to 2, 5 to what? Okay, that was the answer. Okay, so how about the energy? So um, again, the total the energy the of the sumo that was for the we learned before. I'm going to show you the omega t by cosine 2 pi t and square 25 cosine square 2 pi t. So that was it is equal to infinity minus infinity 25 cosine square 2 pi t. That was the positive value. Yes, definitely. This is the periodic. The after integral over the time, and also to increase, the it is going to the infinity. Okay, not going to 0. Why? Because that was the positive. Okay, so for this case, we're going to use, because the energy is going to infinity during the periodic signal, we're going to using the average power instead of the total energy. So that was the what I wanted to do. So again, some students have still being confusing, but so the signal, again, the periodic signal such as sine and cosine have infinity energy due to their continuous repetition over the time. Okay, so that is what we wanted to do. All right. So maybe again, I'm gonna just the summary of the energy signal, the total, the energy signal, and the average the power. Okay, average the power signal. Again, signal of the power and energy classify usually based on total energy and average the power. The energy is the non-periodic like this one, but the energy signal it should be less than the infinity. But the P, the average power, is going to 0. That we're going to call as that was the energy of the signal. Okay, maybe it's again the energy signal has the characteristic infinite the total energy, 0 the average the power. Okay, but the power signal, the average the power has some value, means is non-infinity, but the energy value that was the infinity. So in the previous, the question is the power signal. We can distinguish for the power signal. Okay, that's what we want to do. That was for it's very good questions. Okay, kind of for the test. So they are given to three signal is an energy signal or the power signal. Okay, so step one, we have to distinguish that was the energy signal or power signal. And the second one, we have to evaluate it, normalize the power as appropriate. So the first equation is the W of t. This is the rectangular function, okay? The t over t sub 0. And then the second one was the W over T is the rectangular function multiply cosine omega zero, not omega, the cosine in the W sub zero, the T. And last one, the W over T is equal to cosine square W sub zero, the T here. Okay. So the first one, the energy signal is the T over T and minus T over T. That was for is one value. You know that. So that was finally that was the T sub zero. So that was the energy, the signal, energy signal, because the total energy it is infinity and non-zero. Okay. So how about the second one? The second one that was for we're gonna try the energy. That was for the cosine square because in here they're going to one. Okay, it was going to one. So that was for oops, that's 1 over 2, 1 plus cosine 2 omega 0 t. So we learned before the period of the signal is going to 0. So finally, the 1 over 2, so that was a t sub 0 over 2. So means, again, the total energy is not infinity. That was the energy signal. Okay. So when you see this question, you have to try the both of them. The both of them. Okay, the question C. Okay, that was, we're going to try first the power. Okay, the limit, the t sub 0 is going to infinity. That was the 1 over t sub 0 and t sub 0 over 2 minus t sub 0 over 2. It doesn't matter, okay? So t sub 0 is 0, it doesn't matter. That was the w square over t. That was the cosine 4 to 4 of omega sub 0 t, the dt. So after, we're going to just trigonometric right there. And after that, that was the constant 3 over the 8, 3 over 8. So it means the average power is less than infinity. Yes. Infinity, non-zero power. Yes, that was the power signal. That should be the total energy. The should be the infinity. Okay. Just just try yourself. Okay? Just try yourself. All right, that was the DV. This is also very important for the future communication systems to measure the signal. The DV, the measure for the power ratio, provide relationship between quantities, not actual value, and even quantities, usually based the 10 or sometime 2. That is different. The base logarithmic measure of the power ratio, the ratio of the power level at the output of a circuit compared to width that input is often specified by decibel of the gain. So dB like this one for the power, piece of out over piece of in, and piece of out over piece of in is equal to 10 to dB over 10. So normalize the power like this one, but the piece of, maybe RMS, ISO RMS, that should be the 20. Don't be in the mistake, okay? The power, the 10, the voltage current is like the gain was number 20. For the SNR, yes, definitely, okay? So like this one. So sometimes to effectively calculate it by using the dBm, sometimes I'm using my dBm, that was based on 1 milliwatts over the 1 power. Okay, the power, if the power has a unit as the milliwatts, yes, we have to use that one. Okay, so 1 milliwatts, so 10 to log the 10 1 0 dBm. The 10, yes, the 10 dBm. 0.1, yes, the minus 10 dBm. Okay, that was for the definitions of the power. Okay, all right. All right, so this is the questions. So the question was given, the average reading power meter is connected to the output circuit, the transmitter. The transmitter output is fed into 50 ohm resistive rod, and the watts meter reads 25 watts. So what is the power in the dBm units? What is the power in the dBm units? Okay, so the first one, the dBm, this is the formula. So go back to here. Uh, 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 uh. This is the 25 watts. Okay, this is the 25 watts. So we needed to that make the milliwatts, right? Milliwatt, 0.025 right here. But here we don't need it because they wanted to they have already, we're gonna divide it 0.001. Okay. So the milli, that was for, but some students really being confused. Again, that was still the 25. but that should be divided 0.001, okay, 0.001, and after calculation, 43.98 the dVm. How about the K? The dVK? It's like the 25, the over 1,000. So, so it depends on the value, milli and kilo, we have to divide it, okay? It's right there. So the after calculation, minus 60.02 dVK. So don't missing the K and milli, the after my dB, okay? So second, what is the value dVMV? Okay, dVMV. So dVMV, the first order, we have to start from derivation. P value. P is the power, is formula, V sub RMS square over R. Um, reformat for V sub RMS is equal to root the PR. Okay, and P 25, R is 50. So we're gonna find the voltage from the given and P and R value. But the go back to here. That they're looking for the dB MV. Okay, so dB MV. So sorry, dB MV. Sorry, this is right there. This is number 20. Don't be confusing. The 20 log 35.36 over 10 minus 3. Okay, minus 3. So finally, you're going to get the 90.97 dB MVV. Okay. All right, this is the phasor form. Again, this is the signal, the W over T, that was amplitude, absolute value, the cosine, omega 0 T. This is the function of the phase, but sometimes, that was the theta, like this one. It's up to you. And then that was, the real part. This denotes the real parts of the complex quantity, so the function. So C is, x plus jy, definitely some value. That was very simple, really, really easy one. Like, oops, I'm sorry. This is C. It's the angle. Okay. Complex form, polar form, the phasor form, you have to know. Okay. Complex form, phasor form, exponential. Okay. So just you have to, the transfer from complex form to the phasor form, from the phasor form to exponential form, that is what you have to do. All right. I think the last questions for today. Thank you for your follow with me. The first question, express signal 50 sine 2 pi cos 2 pi 1000 t plus 30° in the phasor form. Okay, so the first over the given signal in the sine form, but the phasor is typically cosine. It's really important phasor form is using the cosine set. Okay, so the sine theta is cosine theta minus 90. So from here, if we wanted to the original sine functions, cosine functions, we have to minus the 90. That was what we wanted to do. So that was the phasor form, but that should be usually the absolute value. Okay. All right. So the other one that was the signal 20 cosine 2 pi f sub 0 t 45 f sub 0 500 hertz express a complex exponential form here. 2 pi f sub 0. This is the radian value 500 radian per second. 1000 the pi radian per second. The question is complex exponential form. So that was cosine omega 0 t plus pi means we have to denote it's like the real value. Okay. Oops. So this is the original, the function 20 cosine over 2 pi f sub 0 t plus 45 from the question, the given signal. The real, the 20, 1000 the pi. Okay. 1000 pi. Why? Because we have already calculation in here plus 45. Okay. All right.